Right now, you are drifting through the largest empty region ever discovered, a cosmic bubble nearly 2 billion light-years wide, where 20% of all matter is simply missing. And here's the unbelievable part. Scientists just confirmed its existence using echoes from the Big Bang itself. The signal is so strong, it is 100 million times more likely to be real than coincidence. This void surrounds Earth, the Milky Way. Everything we have ever known, it has been hiding in plain sight, subtly warping our measurements, confusing our models, and revealing that the universe we live in is far stranger than we ever imagined. If you're enjoying this journey into the unknown, hit that like button because we're about to go deeper. Scientists measure the expansion of the universe by watching galaxies race away from us. They call this expansion rate the Hubble constant, and they calculate it using two methods. The first examines ancient light, the cosmic microwave background, a snapshot from when the universe was only 380,000 years old. This gives an expansion rate of 67 kilometers per second per meg. The second method measures nearby stars and exploding supernova. This gives a rate of 73 kilometers per second per meg, 6 units of difference. Sounds tiny, but in cosmology, it's catastrophic. Both measurements keep getting more precise, and the contradiction refuses to disappear. Nobel laureate Adam Rees said it clearly. Our measurements keep improving, and the tension doesn't go away. This is not a mistake, not instrument error, not bad data. Even the James Webb Space Telescope confirmed the discrepancy. Something fundamental about our universe is wrong. Either the early universe behaves differently than we think, or our local universe is tricking us. Or maybe something far stranger is happening. Scientists call this the Hubble tension. But honestly, that name is too soft. This is a crisis in cosmology. Our best model, lambda CDM, explains almost everything. The formation of galaxies, the abundance of elements, the temperature patterns in the cosmic microwave background. Yet it cannot reconcile these two expansion rates. The tension has passed phi sigma, meaning the odds of this being random are about 1 in a million. For years, scientists hoped it would disappear. Better instruments, more data, sharper analysis. Instead, the mystery got deeper. So what could cause two different expansion rates? The answer might be hidden in the space around us. Before galaxies, before stars, before atoms, the universe was a violent ocean of sound. In the first 400,000 years, space was filled with plasma, a hot, dense fluid of charged particles. Gravity pulled matter inward. Radiation pressure pushed outward. These forces created vast sound waves, exploding through the early universe at half the speed of light. When the universe cooled enough for atoms to form, the waves froze in place, like ripples locked inside ice. These fossilized sound waves became Baryon Acoustic Oscillations, a hidden pattern that shaped where galaxies would form billions of years later. But here's where everything changes. These frozen ripples act like a cosmic ruler, a fixed distance imprinted in the structure of the universe. We know exactly how long this ruler is supposed to be. Yet, when scientists measure it from our position, it looks distorted. Count the galaxies, map their distances, look in every direction. Something is wrong. Within 1 billion light-years of Earth, there are fewer galaxies than expected. The region around us is 15% to 50% less dense than the cosmic average. In 2013, astronomers Keenan, Barger, and Cowie revealed the shocking truth. We live inside a massive underdensity, a void nearly 2 billion light-years across. Some call it the KBC Void. Others call it the local hole. Either way, it's enormous, and the Milky Way sits near the center of it. This changes everything, because living inside a void makes galaxies outside it appear to rush away faster than they really are, which means our local environment may be bending our measurements, creating the Hubble tension. And if that's true, then the expansion rate we observe nearby isn't universal. It's influenced by the structure of the cosmic web around us, a silent transformation shaping our understanding of the universe, a hidden structure reshaping the numbers, and a reminder that reality is far more complex than empty space and simple expansion. The universe is whispering secrets through the void we call home, and this is only the beginning. Astronomers once believed that if we were standing near the edge of a cosmic void, the universe would look lopsided. More galaxies in one direction, fewer in another. But that's not what we see. Instead, the underdensity around us wraps the sky almost like a perfectly shaped bubble carved out of the cosmic web. Different instruments, optical telescopes, infrared surveys, X-ray missions, radio arrays, all agree on the same unsettling truth. Nearby space has fewer galaxies than it should, and faraway space has more. The pattern is undeniable, but the real question strikes deeper. How can a region this enormous, this empty, even exist? And what does it mean that we are inside it? Imagine removing 1 out of every 5 galaxies in the universe around you. Now remove 1/5 of the dark matter, the invisible scaffolding that holds cosmic structure together. That is what it means to live inside the KBC Void. 20% below average density, a tiny number at human scale, but a colossal void at cosmic scale. To understand the consequences, you have to think in terms of gravity, the quiet architect of the universe. Where matter gathers, gravity deepens like a valley. Where matter thins out, gravity rises like a hill. Galaxies naturally roll down the valleys and drift away from the hills. A void is a gravitational hill, a swollen, gentle rise in the fabric of spacetime that slowly pushes everything outward. And the KBC Void has been pushing for 14 billion years. As the void expands, its influence becomes measurable. The flow of galaxies, the shape of cosmic structures, even the expansion rate we think describes the entire universe. Because inside a void, space expands more freely, with less matter to slow it down. So when we measure the recession speed of nearby galaxies, we aren't seeing the universe's true, average expansion. We are measuring a special place. Like taking the temperature of Death Valley and declaring the whole planet a desert. We are standing in a locally hot spot in the cosmic landscape, a region that expands faster than the cosmic average. But here comes the contradiction. Our standard cosmology, the SEIDEME model, predicts that on scales of hundreds of millions of light-years, the universe should average out small bumps and wrinkles. Sure, but a void 2 billion light-years wide with a 20% density deficit that should not exist. Some calculations put the probability at 1 in a billion, a cosmic accident of impossible scale, yet every measurement says the same thing. We live in an underdense region, so we face 3 possibilities. We are spectacularly unlucky. We live in one of the rarest environments in the entire universe. Our cosmological model is incomplete. Something fundamental is missing from our equations. Voids like this are more common than we think, and the universe is far clumpier than SEIDEME predicts. And here's where the story becomes even stranger. Voids don't sit still. They evolve. They evacuate. Surrounding dense regions tug on everything inside the void. Galaxies near the boundary feel it first. They accelerate outward, leaving the void emptier than before. That deepens the gravitational imbalance, which accelerates more galaxies outward. A feedback loop stretching across billions of years. Observations show this is not theory, it's happening right now. Entire rivers of galaxies flow outward at 400 kilometers per second, over distances of hundreds of millions of light, and the Milky Way is one of them. Our galaxy is sprinting away from the void's center at 250 kilometers per second, nearly 1 million miles per hour. We are escaping, and that escape motion has consequences. When a galaxy moves, its motion adds to or subtracts from the cosmic expansion signal. Inside the void, most galaxies are moving outward, which means their redshifts are artificially boosted. So when astronomers calculate the Hubble constant using nearby galaxies, they're not measuring the universe's expansion. They're measuring the expansion plus the void's push. Indronil-Banek's calculations showed the void can inflate our measurement by about 11%, astonishingly close to the exact discrepancy between local supernova measurements and the cosmic microwave background. It all fits, but only if we are near the void center. If we were at the edge, the expansion would look uneven, faster in one direction, slower in another. But it looks uniform, meaning we are within a few 100 million light-years of the center. What are the odds? Living in a rare void is unlikely. Living at its center is even stranger, unless something about void centers makes them more likely to host observers. A quiet, uncomfortable whisper of an anthropic argument. But the universe doesn't care whether the explanation makes us uneasy. It simply is what it is. Measuring expansion inside a void is like standing on a moving walkway. Everyone walking toward you seems faster, not because they are, but because the ground beneath you is shifting. Inside the KBC Void, the universe is stretching, flowing, and evolving around us, shaping every measurement we make. The numbers are real. The interpretation is what we must reconsider. Local conditions matter more than we like to admit. Here's what really happens. Light from a distant galaxy begins its journey across the cosmos. As it travels, space itself expands, stretching the wavelength of the light. This stretching is redshift. The more stretching we see, the more expansion has occurred during the light strip. But inside a cosmic void, everything becomes more complicated. A galaxy inside a void isn't just receding because the universe expands. It's also falling outward. flowing toward denser regions just beyond the void's boundary. This motion, this evacuation of the void, also increases redshift. But today's instruments can't separate these two effects. Most astronomers take a shortcut. They assume all redshift comes from expansion alone. They plug the numbers into their equations, and they get a Hubble constant of 73 instead of 67. The value inferred from the cosmic microwave background. It looks like a mystery. It isn't. It's simply void dynamics masquerading as faster expansion. Indra Nelbanik explains it with a powerful analogy. Imagine the universe as a vast landscape. Dense regions are valleys, voids are hills, and galaxies roll downhill from the hills into the valleys. This motion isn't expansion, it's falling. But redshift cannot tell the difference. Both falling and expanding stretch light in almost exactly the same way. The only way to detect the difference is statistical. Measure enough galaxies in enough directions, and a pattern starts to appear. A pattern that matches exactly what we see. Inside the void, local expansion measurements are systematically inflated, far beyond the void. The inflation vanishes at high redshifts, where observations sample the distant universe. The so-called Hubble tension disappears entirely. The CMB measures the true average expansion of the whole universe. Local measurements capture only the expansion inside our void. Both are correct. They are simply measuring different environments. But accepting this explanation is uncomfortable. It means we live in a statistically unusual region, not special in a philosophical sense, just not representative of the cosmic average. It means cosmology becomes harder. We must account for local anomalies before claiming fundamental physics is broken. Many scientists resist this conclusion. Some prefer new physics, early dark energy, modified gravity, time-varying dark energy equations of state. All of these are possible, but far more complex. They require inventing new phenomena. The void explanation uses only standard physics, gravity, density, variations, and motion through space. Occam's razor gives a clear hint. The simpler explanation deserves serious attention. And now the evidence is overwhelming. 20 years of data, hundreds of measurements, Baryon Acoustic Oscillations observed across billions of light, galaxy surveys mapping the cosmic web, peculiar velocity measurements showing bulk flows. Every independent dataset points toward the same conclusion. We live in an underdense bubble. Researchers tested this directly. They compared a model where the universe is perfectly homogeneous, calibrated to CDM and Planck CMB. Results a model that includes a void matching the properties of the KBC Void. Then they asked, which model better fits the real bow data? The result wasn't close. The void model is approximately 100 million times more likely than the void-free model. Yes, these are not a typo. For comparison, particle physicists require 5 sigma to claim a discovery, a probability of only 1 in 3.5 million that the result is random. The void evidence exceeds that by orders of magnitude. And the key point: this wasn't cherry-picked. Researchers didn't assume a void exists and then look for supporting evidence. They fed 2 decades of bow measurements into the models and simply asked, does including a void improve the fit? It did, dramatically, consistently, unavoidably. Every line of evidence now points in the same direction. Our local cosmic neighborhood is an underdense region, a giant void, and that void is distorting our measurements of the universe. Local conditions matter more than we ever imagined. Picture this. A beam of ancient light leaves a distant galaxy, traveling across billions of years of expanding space to reach us. As it moves, the universe stretches its wavelength, imprinting the unmistakable signature we call red. Astronomers treat that redshift as a clean signal, the pure fingerprint of cosmic expansion. But inside a giant cosmic void, that assumption breaks down. Because here, galaxies don't just drift away with expanding space, they move. They're physically flowing outward, falling toward denser regions, like water draining from a massive bowl carved into the cosmic landscape. And this motion adds extra redshift, a subtle distortion that hides inside the data. Modern telescopes can't pull these two effects apart. Expansion and motion blend perfectly. What looks like the universe racing away faster might just be galaxies escaping our underdense bubble. Astronomers assume all redshift is expansion. They plug the numbers into their equations. They calculate the Hubble constant, and they get 73 instead of 67. A mystery emerges, but maybe not a mystery at all. It's void dynamics, masquerading as faster expansion. Indra Nelbanik explains it with a simple analogy. Imagine the universe as a vast landscape of hills and valleys. Dense regions are deep valleys, where gravity pulls strongly. Voids are high hills, places where gravity is weak. Galaxies naturally fall from the hills into the valleys. Their motion isn't expansion. It's gravity pulling them downhill. But redshift can't tell the difference. Both stretch light in exactly the same way. The only way to detect the effect is through statistics, by measuring enough galaxies in enough directions to see patterns emerge. And the pattern does emerge at low redshifts, meaning our local region, expansion appears faster. At higher redshifts outside the void, the effect fades and the numbers drift back toward 67. This is exactly what astronomers observe. The cosmic microwave background, which samples the entire universe, gives the global truth. Local measurements sample the inside of our bubble. Both are correct. They're just measuring different realities, but accepting this leads to an uncomfortable truth. We live in a statistically unusual location, not special in a metaphysical sense, but special in a way that complicates the measurement of the universe. Cosmology becomes harder because our neighborhood is not typical. Some researchers resist this conclusion and turn instead to exotic physics. Early dark energy, modified gravity extra neutrinos, dark radiation, time-varying dark energy equations of state. Elegant ideas, but complex, speculative, and unsupported by direct evidence. The void explanation uses only known physics, gravity, motion, density, variations, no extra ingredients needed. And the evidence keeps growing. 2 decades of galaxy surveys, Baryon Acoustic Oscillation maps, bulk flow measurements, and redshift catalogs all point to the same conclusion. The KBC Void isn't hypothetical, it's observable. An underdense bubble stretching nearly 2 billion light-years across surrounds us, and it changes how we measure the universe. Statistical analysis, comparing two cosmological models. One uniform, one with a void found something astonishing. The void-based model is 100 million times more likely to match real observational data. This isn't handpicking evidence or bending results. Researchers fed decades of bow measurements into both models and asked which one the universe prefers. And the universe answered loudly. The uniform model struggles. It can't match galaxy distributions. It can't match expansion variations across regions. It can't match clustering scales. But the void model explains all of them at once, without rewriting the laws of physics. Yet science is never absolute. Alternative explanations remain possible. Maybe systematic errors are hiding in our instruments. Maybe multiple unrelated coincidences mimic the effects of a void. Maybe dark energy behaves differently than expected. But these alternatives require extra assumptions. The void requires none. Occam's razor leans heavily in its direction. Without a void, the universe simply doesn't make sense. The models struggle, the numbers fight each other, and reality refuses to match our expectations. Galaxy distributions twist away from predictions. The cosmic distance ladder, one of astronomy's proudest achievements, shows cracks and inconsistencies. Expansion measurements change depending on where you look, as if the universe itself is giving contradictory answers. Standard cosmology can't explain it, but the moment you place a giant cosmic void around us, everything snaps into place. Suddenly, the models behave. Galaxy clustering patterns match observations almost perfectly. The infamous Hubble tension evaporates without introducing new particles or rewriting gravity. And the large-scale bulk flows, entire rivers of galaxies streaming across space, finally have a cause. They're re-rushing toward the denser edges of our underdense bubble. But in science, high probability is not certainty. There's always room for alternative ideas. Maybe countless, tiny, systematic errors all happen to point in the same direction. Maybe the universe tricked us with layered coincidences. Maybe dark matter acts differently in certain regions, or dark energy changes with location, or quantum effects ripple across cosmic distances. These ideas are possible, but they require far more assumptions than the simple explanation. Because the simplest explanation is this: we live inside a void. And the evidence supporting that idea has become so strong that ignoring it means rejecting basic statistics. Yet some scientists do exactly that. They object on philosophical grounds, saying a void this large is too rare, too unlikely. That we couldn't possibly be inside one, but rarity is not impossibility. Someone always wins the lottery, even if the odds are 1 in 100 million. Unlikely planets exist. Rare biological mutations happen, and maybe, just maybe, conscious observers are more likely to appear in regions where galactic conditions are stable enough for life. It's the anthropic argument, uncomfortable for some, but not unscientific. For more than 10 years, The Hubble tension has been cosmology's deepest embarrassment. 2 methods, 2 answers, separated by 9 kilometers per second per megaparsec. Entire careers were built trying to locate the error. New instruments were engineered to hunt the discrepancy. Theoretical physicists proposed wild new physics, early dark energy, variable constants, modified gravity, sterile neutrinos, dark radiation, interacting dark energy, decaying dark matter, endless, exotic explanations for something that may not have been a mystery at all, because the void offers a clean solution using nothing but standard physics. Think about what each method actually measures. The cosmic microwave background method looks at ancient light, minus 380,000 years after the Big Bang, coming from all directions simultaneously. It samples the entire observable universe. That light carries the imprint of density, temperature, composition, and early expansion. Feed this data into lambda CDM. Evolve it forward 13.8 billion years, and you get an expansion rate of 67.4. A global truth. A universal average. The local method, however, sees something completely different. It measures the pulsations of Cepheid variable stars in nearby galaxies, just tens of millions of light years away. Then it uses Type Ia supernova in those same galaxies to calibrate distances. Then it pushes out to a few billion light years, using more supernova. Combine distance with redshift, and the expansion rate emerges, 73.04. But this entire measurement happens within the KBC void. It never leaves our cosmic bubble. So, the 2 methods are not measuring the same universe. Imagine one scientist measuring human height only in the Netherlands, a place where people are unusually tall. Another scientist measures height across the entire world. The Dutch sample gives you 183 centimeters. The global sample gives you 171. Both are correct. Both are honest. Both use precise measurements. They're just sampling different populations. That is the Hubble tension. Not a contradiction, a misunderstanding of context. And inside the void, galaxies evacuating the region have extra motion added on top of expansion. Their outflow increases redshift. The lower matter density speeds up local expansion. The gravitational gradient bias. All measurements in the same direction. Banach's calculations show the effect inflates the Hubble constant by around 11%. Add 11% to 267, and you end up at 74, exactly the local value. No new physics required. Some details remain unknown. The void's exact size and density must be charted more precisely. We need a more accurate map of the Milky Way's position inside it. Competing explanations still need rigorous testing, but the mechanism is clear and testable. If the void explanation is correct, several predictions must come true. Beyond about 3 billion light-years, the Hubble constant should drop towards 67. The tension should fade at large distances. We should see mild directional asymmetries. Where the void isn't perfectly, bulk flows should align with the expected evacuation pattern, and upcoming telescopes are perfectly suited to test this. The James Webb Space Telescope can measure Cephidas at unprecedented distances. The Vera Rubin Observatory will map billions of galaxies in exquisite detail. Euclid will chart Baryon Acoustic Oscillations across cosmic time. Within a decade, the void hypothesis will be confirmed or ruled out decisively, and if confirmed, the Hubble tension ends, not through exotic breakthroughs, but through something much more humbling. Location matters. Measurements inside a cosmic bubble don't represent the universe as a whole. Cosmologists have to adjust for our environment, just as a meteorologist would adjust if all their weather stations were placed inside a desert. We're not at a special location in the universe. We're at an unusual one, a place that complicates measurements, but doesn't break physics. Voids can't be seen directly. They're defined by absence. Astronomers look for what's missing, not what's there. Counting galaxies across enormous datasets, measuring distances and velocities with extreme precision, running statistical analyses across millions of cubic regions of space. Most cubes contain similar galaxy numbers. Some hold clusters, some hold filaments, and some occasionally hold far fewer galaxies than average. Those regions are voids, and we live inside one. String together enough underdense regions, and a void emerges, not empty space, but a structure defined by absence. Astronomers first discovered these cosmic hollows back in when the earliest redshift surveys revealed the universe shaped not like a uniform fog, but like a vast web of filaments, knots, and bubbles. Dense clusters where filaments intersect. Long, glowing threads of galaxies stretching across millions of light, and between them, enormous gaps, voids like bubbles in cosmic foam. A pattern began to appear, and as surveys improved, The same pattern grew sharper. The KBC Void showed up independently in project after project. The 2DF Galaxy Redshift Survey, the Sloan Digital Sky Survey, the 2MASS Catalog, tens of thousands of galaxies mapped in 3 dimensions. Distances measured, redshifts, recorded, every dataset whispered the same truth. Galaxy density drops around the Milky Way. We are sitting inside an underdense bubble, but mapping galaxies is just the beginning. There's another way to reveal hidden structure. Motion. Every galaxy carries 2 kinds of velocity, one from expansion, predictable, proportional to distance, another from gravity random, chaotic, but full of clues. Subtract the expected expansion, and what remains exposes the universe's gravitational landscape. Overdense regions pull, underdense regions push, and when astronomers tracked these peculiar velocities across tens of thousands of galaxies, a stunning pattern emerged. Galaxies near our void's boundary are rushing outward faster than expansion alone can explain. Those deeper inside drift more gently. It's exactly the flow pattern predicted for a void nearly 1 billion light-years across. Then came the third line of evidence. Baryon Acoustic Oscillations, frozen sound waves from the early universe that left behind a preferred spacing between galaxies, like ripples on a frozen lake. That spacing should appear the same everywhere, unless something distorts it. And something does. A void adds extra redshift. It stretches the apparent Bow scale in ways we can measure. After 20 years of surveys, optical, infrared, ground-based, space-based, every one of them shows the same distortion, subtle, consistent, impossible to ignore. Another clue lies in the cosmic microwave background. Photons traveling through gravitational hills and valleys gain or lose energy. This is the integrated Sachs-Wolf effect. Dense clusters imprint warm spots, voids imprint cold spots, and if our local region is truly underdense, it should leave a fingerprint on the CMB in a specific direction. Observations hint that this signature is there, faint but present, waiting for high-resolution missions to confirm it. Even gravity itself testifies. Mass bends, space-time, warping, and delaying the paths that light takes. Strong lensing reveals massive structures. Weak lensing reveals subtle distortions, and voids reveal something quieter. Too little bending, too little mass. Mapping these patterns requires enormous sky coverage and staggering precision, the kind Euclid and the Vera Rubin Observatory were built for. Their data will either erase the void theory or etch it in stone. Piece by piece, these methods converge. Galaxy distributions, peculiar velocities, bow distortions, CMB imprints, lensing signatures, independently collected, independently analyzed, yet all pointing to the same conclusion. The local universe is under. The bubble extends roughly 1 billion light-years in every direction. It influences galaxy motion, clustering, even the light from the beginning of time, because the beginning still surrounds us. 13.8 billion years ago, the universe cooled just enough for electrons and protons to hold on to each other. Neutral hydrogen formed, and the fog lifted. Photons, previously trapped in an endless haze of scattering, finally broke free. They have been traveling ever since, filling the cosmos with a nearly perfect glow. The cosmic microwave background, uniform to 1 part in 100,000. Yet those tiny temperature variations matter more than anything else. Slightly hotter regions mark slightly denser beginnings, slightly cooler regions mark the seeds of future voids. Gravity magnified those early imperfections. Dense patches grew into clusters and thin regions expanded into caverns of nothingness. And the Planck satellite mapped this ancient light with insane precision, giving us the initial conditions of everything we see today. And when those initial conditions are evolved forward in time, using nothing but standard physics, they produce something remarkable. Voids. Exactly the kind we observe. Exactly the kind we live in. The universe is not made of what we see. Not even close. Only 5% of everything is normal matter. The atoms that build stars, planets, oceans, you, me. 27% is dark matter, an invisible scaffolding holding galaxies together. And the remaining 68% is something even stranger. Dark energy, a force accelerating the expansion of the universe. These numbers aren't guesses. They're written into the cosmic microwave background, the faint afterglow of the Big Bang. The pattern of tiny hot and cold spots, the way they correlate across the sky, the statistical structure hidden inside those temperature ripples. All of it encodes the universe's ingredients with astonishing precision. From this ancient light, scientists calculate not only what the universe is made of, but how curved space is. how fast the universe expanded in its early years, how matter and radiation evolved, and ultimately, what the expansion rate should be today. Every major experiment agrees. Planck 267.4 kilometers per second MPC. WMAP nearly identical. The Atacama Cosmology Telescope, the South Pole Telescope, same result. All of these instruments sampled the entire sky. The photons they detect left matter at redshift 1100 more than 13 billion years ago. They come from every direction equally. They reflect the universe averaged together. But the cosmic microwave background has a blind spot. It cannot tell us what is happening locally. It cannot see small-scale lumps, dips, and enormous regional variations. It only sees the cosmic mean. The assumption behind standard cosmology, the cosmological principle, says the universe is roughly uniform on large scales. Smooth, even, homogeneous. But the KBC Void challenges this idea. A 2 billion light-year underdensity is not a small wrinkle. It's a structural feature on a scale large enough to shift measurements. If we live inside a void, then local expansion will always appear faster than the global cosmic average. The cosmic microwave background tells us the Earth-wide forecasts. Local measurements tell us today's weather. Both can be true at the same time. Some scientists have tried to constrain local voids directly from the CMB, searching for patterns that would betray our position inside an underdensity. The results hint at something, but the CMB's resolution simply isn't fine enough. By the time those photons reach us, they've crossed so much cosmic distance that nearby structures are smeared into invisibility. Better clues come from combining early universe data with galaxy surveys. The CMB gives the starting conditions, galaxies show how those conditions evolve, and in our region, evolution seems to have produced a genuine underdensity, a bubble where matter is thinner, galaxies sparser, and expansion slightly faster. This isn't a failure of the cosmic microwave background. It is evidence that the universe around us isn't the same as the universe, on average. And speaking of measurements, some stars act like cosmic beacons, revealing distances with incredible consistency. Cepheid variables, enormous, unstable yellow supergiants, pulse in and out like beating hearts. When they expand, they brighten. When they contract, they dim. The rhythm is perfect and mathematical. Brighter Cepheids pulse more slowly. Dimmer ones pulse faster. Henrietta Swan-Leavitt discovered this relationship in 1912, and it became the cornerstone of the cosmic distance ladder. Here's how it works. You watch a Cepheid, you measure its pulsation period. That period reveals its true brightness. Compare true brightness to how bright it looks from Earth, and you know exactly how far away it is. The challenge is simple. Cepheids are rare, and beyond a certain distance, individual stars blur into the glow of their host galaxies. Finding a single Cepheid millions of light-years away requires the Hubble Space Telescope, or something even more powerful. But without them, we couldn't measure distances to nearby galaxies. And without those distances, we couldn't calibrate supernova. And without supernova, we couldn't measure the expansion of the universe directly. Cepheids are the bridge. They connect the scale of our galaxy to the scale of the cosmos. And crucially, they measure distances inside the void, which is exactly why the numbers don't match the cosmic microwave background. The SHOES Project Supernova, and ACHE for the equation of state, has spent decades chasing one question. How fast is the universe really expanding? To answer it, they rely on one of the most powerful techniques in cosmology. Pairing Cepheid variables with Type Ia supernova. Type Ia supernova are exploding white dwarfs, titanic blasts, so bright they can outshine billions of stars. Even better, they explode with nearly identical peak brightness. They're cosmic lighthouses. Perfect, standard candles, but only if you know exactly how bright they truly are. That's where Cepheids enter the story. Find a galaxy that contains both Cepheids and a Type Ia supernova remnant. Use Cepheids to measure that galaxy's distance with precision. That measurement becomes the calibration for the supernova's true brightness. Repeat this over and over across many galaxies, and suddenly the supernova become rulers capable of measuring billions of light. Adam Rees and the SHOES team had been doing exactly this. Over 1,000 dozens of Type Ia supernova. Uncertainties below 2%, a level of precision unheard of in cosmology. When the James Webb Space Telescope launched, Rees used it as the ultimate test. Webb's infrared vision slices through cosmic dust. Its razor-sharp resolution separates tightly packed stars that Hubble might blur together. If Hubble introduced errors, Webb would expose them instantly. But Webb didn't. Webb confirmed everything. The Hubble constant still reads 73 kilometers per second per megaparsec. The tension didn't shrink. It got worse. Critics tried everything. Maybe Cepheid brightness gets distorted in crowded starfields. Maybe dust absorbs light more unpredictably than models assume. Maybe Cepheids behave differently in different galactic environments. But every alternative failed. The measurements remain stubbornly solid. Here's the twist. Cepheids only reach out to around 130 million light. Every Cepheid ever used for calibration sits inside the KBC Void, our underdense cosmic neighborhood, meaning they are not measuring the global expansion of the universe. They're measuring the expansion inside our bubble, where space stretches faster than average. Type Ia supernova go farther, billions of light years. But their calibration starts inside the void. So the local expansion rate gets baked into every distance calculation. It's not wrong. It's context-dependent. Cepheidites beautifully mapped local structure. They cannot map the cosmic mean. To reach the true global value, we need measurements that sample the entire universe, like the cosmic microwave background or Baryon Acoustic Oscillations. At large distances, science loves tension. It thrives on competing ideas, on data that refuses to cooperate, on numbers that refuse to align. But around 2015, the Hubble tension crossed from interesting discrepancy into full-blown crisis. Before that, uncertainties were big enough to pretend everything might still match, but as the data sharpened, Planck, Hubble, supernova surveys, the two values drifted apart in a statistically undeniable way. By 2018, the mismatch hit 3 sigma odds of a fluke, to 1 in 400. By 2019, it surpassed 5 sigma nods. Una pulgada, 3.5 million. The level particle physicists used to declare a discovery, cosmology, had a problem. Theorists proposed sweeping new physics. Early dark energy, modified gravity, evolving equations of state, interactions between dark matter and dark energy, extra-relativistic particles, exotic quantum effects at cosmic scales. Each idea fixed one problem, but broke 3 others. Lambda C, DM, the standard model, kept passing every test, except this one. Experimentalists tore their instruments apart metaphorically. Was the Hubble Space Telescope off by a tiny amount? Was Planck miscalibrated? Were supernova observations distorted by atmospheric effects? Years of checking found nothing. So, when the James Webb Space Telescope returned the same value, -73, the crisis deepened. Some scientists whispered the unthinkable. Maybe the cosmological principle, the idea that the universe is uniform on large scales, is wrong. Not mythology, not philosophy. Just an assumption we've held for a century. If the universe isn't perfectly uniform, if our cosmic neighborhood is unusual, if we happen to sit inside a giant underdense bubble, then the tension dissolves instantly. But that idea makes people uncomfortable. Humans spent centuries believing we were the center of creation. Modern cosmology humbled us. Earth is ordinary. The sun is ordinary. The Milky Way is ordinary. So suggesting our location might be special feels like a step backward. But it's not philosophical specialness. It's statistical specialness, the kind that occasionally happens in a vast universe. Sometimes someone wins the lottery. Sometimes a star forms in a bizarre orbit. Sometimes galaxies cluster in rare configurations. And sometimes, intelligent observers arise inside a cosmic void, simply because that S-ware conditions make their emergence more likely. The evidence for the KBC Void keeps growing. It's no small ripple. It's a megastructure, billions of light years wide, reshaping every nearby measurement we make. And if we live inside it, the Hubble tension was never a crisis. It was a clue. Have you ever wondered why some regions of the universe have far fewer galaxies? Enter the voids. Enormous cosmic emptiness. Huge voids, like the KBC Void, might actually offer conditions favorable for life. Lower density could mean fewer galaxy collisions, less radiation, and more stable environments for complex chemistry. These are, of course, speculations, but not unreasonable ones. The void explanation is also appealing because it requires no new physics. Voids exist, their dynamics are well understood, and they impact measurements exactly as observed. No exotic particles, no modified gravity, no early dark energy, just standard cosmology applied carefully, accounting for local structure. Yet some scientists remain unconvinced. If we really are inside a massive void, does that mean the lambda cold dark matter, say the MA model, is correct, or does it suggest the model needs adjusting to allow larger structures? The answer is subtle. CDMA accurately describes the average cosmic evolution. It successfully predicts the cosmic microwave background, explains structure formation, and accounts for matter distribution. But it may underestimate variance on the larger scales. Computer simulations of structure formation are limited in volume and resolution. They can't simulate the entire observable universe in full detail. Maybe rare, but real structures, like the KBC Void, are simply missed. Maybe voids this large are improbable, but not impossible. Or perhaps our understanding of structure formation contains small errors that compound across cosmic scales. Sometimes, the secrets of the universe are hidden in emptiness, and the KBC Void is a striking reminder of just how much we still have to learn. Have you ever wondered why some regions of the universe are so empty? Almost eerily so? Enter the voids. Vast cosmic expanses, where galaxies are sparse. The anthropic perspective suggests observers like us must exist somewhere, and perhaps these voids offer conditions more favorable for life. Lower density could mean fewer galaxy collisions, less radiation, and more stable environments for complex chemistry. It's speculative, yes, but not unreasonable. The void explanation is appealing because it doesn't require any new physics. Voids exist. Their dynamics are well understood, and they influence measurements exactly as we observe. No exotic particles, no modified gravity, no early dark energy, just standard cosmology carefully applied, accounting for local structure. Still, some scientists find this explanation unsatisfying. If we are truly inside a void, does that validate the lambda called dark matter? Say the model suggest it needs adjustment for larger structures? The answer is subtle. CDMA accurately describes average cosmic evolution, predicts the cosmic microwave background, explains structure formation, and matches matter distribution, but it may underestimate variance on the larger scales. Simulations of structure formation are limited in volume and resolution. They can't model the entire observable universe in high detail. Maybe rare but real structures, like the KBC Void, are simply missed. Perhaps voids this large are improbable, but not impossible. Or maybe small errors in our understanding of structure formation compound across cosmic scales. Resolving the Hubble tension won't come from a single observation. It requires synthesizing evidence from multiple sources. Galaxy surveys mapping the void's extent, bulk flow measurements tracking matter motion, Baryon Acoustic Oscillations revealing expansion history in different regions, and supernova distances reaching beyond the void's edge. The data is coming within a decade. We may know whether the void explanation holds. If it does, the crisis ends. If not, the mystery deepens. Now, try to wrap your mind around the scale. The KBC Void spans roughly 2 billion light-years, from edge to edge, a sphere so vast that light itself takes 2 billion years to cross it. In astronomical units, that's 600 mega. For context, the Milky Way is just 100,000 light-years across. The void is 20,000 times wider. Our local group, containing the Milky Way, Andromeda, and dozens of smaller galaxies, spans about 10 million light-years. The void is 200 times wider. Even the Laniakea. This is no small cosmic feature. It's among the largest structures known. Only a few voids exceed it in size. The Boats Void, discovered in 1981, spans 330 million light-years, and is nearly spherical, with far fewer galaxies than expected. Eridanus's Void reaches 1.8 billion light-years across. The KBC Void rivals these supervoids, but here's a difference. We live inside it. Measuring dimensions from within is challenging. Imagine standing in a forest, trying to determine where it ends. You can count nearby trees and notice when density drops, but defining exact boundaries requires surveying vast areas. Cosmologists do the same with galaxies. They divide space into spherical shells at increasing distances, count galaxies in each shell, and calculate average density. When density rises above a certain threshold, to void ends. Current measurements place the KBC Void's edge roughly 1 billion light-years away in most directions, with uncertainty. Maybe 800 million in some directions, maybe 1.2 billion in others. Voids aren't perfect spheres. They have irregular boundaries shaped by surrounding structures. The local sheet, a concentration of galaxies, including the Milky Way, forms one boundary, acting like a wall. On the opposite side, other superclusters define the far edge. The center is also uncertain. Initial estimates place it within a few 100 million light-years of the Milky Way. Determining the exact center requires mapping the full 3D shape by surveying galaxies in all directions to several billion light. Projects like the Sloan Digital Sky Survey and the 2 Micronal Sky Survey have done much of this work, but gaps remain. Some regions are obscured by galactic dust or undersampled due to limited observation time. New surveys will fill these gaps. What is clear? The void contains far less matter than average space. Estimates range from 15% to 50% below cosmic mean density, depending on location. Near the center, density may be 40% below average. Near the edges, perhaps only 20%. This gradient matters. Steeper gradients mean stronger gravitational pull from outside, faster matter evacuation, and larger expansion rate distortions. Mapping it precisely is key to understanding the void's impact on the Hubble constant. The void isn't empty. It contains the Milky Way, Andromeda, about 30 smaller local galaxies, and much of the Laniakea supercluster, with over 100,000 galaxies. Yet, compared to a typical region of this size, it is about 20% underpopulated. Imagine a city where every fifth building is missing. It still functions, but noticeably that's the KBC Void. Still full of galaxies, just not as full as expected. The formation of such a void is complex. Standard cosmology explains that large voids emerge from small density fluctuations in the early universe. Over billions of years, underdense regions expand faster than their surroundings, leaving vast, emptier spaces, like the KBC Void, which continues to shape local cosmic measurements. Slightly underdense regions of the universe expand faster than average. Matter flows from them toward denser areas, and over billions of years, these underdense regions become emptier. But forming a void as large as the KBC requires extremely rare initial conditions, large-scale fluctuations perfectly phased, random quantum variations during inflation. The universe's earliest exponential expansion can occasionally produce such fluctuations. However, lambda, cold dark matter, say the EMA calculations, suggest voids this large should be exceptionally uncommon. This is a tension within the Hubble tension itself. The void may help explain the Hubble discrepancy, yet its existence challenges standard cosmology. The universe began almost perfectly smooth, with tiny quantum fluctuations, 1 part in 100,000 creating regions, with slightly more or less matter. Gravity amplified these differences. Dense regions attracted more matter, growing denser, while underdense regions lost matter and grew emptier. This process, known as gravitational instability, is the fundamental driver of cosmic structure. In the first few 100 million years, the densest fluctuations collapsed into the first stars, which pulled in surrounding gas. These stars formed protogalaxies, which merged into galaxies. Galaxies grouped into clusters, connected by filaments, while voids occupied the spaces between filaments. Think of a soap foam. Galaxies form the bubble walls, and voids fill the interiors. Voids continue evolving. A young void, around 2 billion years old, contains scattered galaxies slowly drifting outward, pulled by gravity from surrounding filaments. By 5 billion years, the void is larger and emptier. By 10 billion years, the void is vast, its interior containing very few galaxies, and its density can be half the cosmic average or less. Dark energy accelerates this process. In dense regions, gravity resists expansion, but in voids, expansion accelerates unchecked, making voids grow faster than the average universe. Eventually, voids will dominate cosmic volume. Trillions of years from now, the universe will be mostly empty space with sparse islands of matter. At the current age of 13.8 billion years, voids occupy roughly 80% of space, but contain only 20% of Tiamat. The KBC void appears mature, suggesting it started from a large-scale early universe fluctuation. Standards say the cosmology grows structure bottom-up. Small fluctuations collapse first and merge into larger structures, naturally producing voids between collapsed regions. But growing a void as large as the KBC requires rare large-scale initial fluctuations. Alternative theories such as modified Newtonian dynamics, MOND, or hot neutrino dark matter models can produce large voids more readily. Whatever the model, voids form naturally, and their dynamics are well understood. The real question is whether voids as large as the KBC are expected, and whether living inside one is coincidence or reveals deeper truths about observation. The Milky Way is not alone. It lies within the local sheet, a vast flat structure extending hundreds of millions of light-years shaped like a pancake. Dozens of galaxy groups, including the Local Group, the Maffei Group, and the NGC 3073 Group, inhabit the sheet. These groups move together in response to large-scale gravitational fields. The local sheet forms one boundary of the local void, a smaller emptiness, within the larger KBC void. Voids grow by evacuating matter toward their edges. That matter doesn't disappear. It accumulates along boundaries, forming sheets and filaments. The local sheet is such an accumulation, Observations show the sheet moving outward from the local void center at roughly 260 kilometers per second, nearly 600,000 miles per hour. This is void evacuation in action. However, the sheet does not move uniformly. Gravitational interactions with neighboring structures create complex motions, stretching and distorting it. Over time, the sheet will disperse, and individual galaxy groups may join nearby superclusters along their own trajectory. Over billions of years, some galaxies in the local sheet will drift into intergalactic space. Eventually, the sheet might no longer exist as a coherent structure. For now, it marks a transition zone. On one side, the low-density local void. On the other, regions of average or higher cosmic density. Crossing from the void into the sheet, galaxy counts increase noticeably. The boundary isn't sharp, there's no sudden wob at a gradual transition. Perhaps 50 million light-years wide, where density slowly rises. Still, the effect is real. Stand in the sheet and look toward the void. Relatively few galaxies appear. Look in the opposite direction, away from the void, and galaxies become far more numerous. This asymmetry has important implications. If astronomers surveyed only in one direction, they could miss the void entirely. Comprehensive all-sky surveys are essential to detect such large-scale structures. The local sheet also influences the motion of the Milky Way. Our galaxy doesn't just orbit within the local group. The entire local group moves together in the sheet's bulk flow, evacuating the local void. This motion affects measurements of cosmic expansion. When we observe galaxies and their redshifts, we are implicitly comparing their velocities to ours, but our velocity includes the local sheet's evacuation flow, introducing systematic biases. Galaxies in the direction we are moving appear slightly blue-shifted compared to expansion predictions, while galaxies in the opposite direction appear slightly red, averaged across the sky. This bias may cancel, but if observations favor certain directions, the effect persists. Careful analysis must account for the local sheet's motion. Fortunately, we can measure it using the cosmic microwave background CMB. Our movement relative to the CMB creates a dipole pattern. Slightly hotter in the direction of motion, cooler opposite. This measurement reveals the local group moves at roughly 630 kilometers per second relative to the cosmic reference frame. This velocity includes the local sheet as bulk flow, plus contributions from larger structures, like the Lania Hias. Subtracting these components allows astronomers to correct expansion measurements for local peculiar velocities, though uncertainties remain. Cosmic velocities are staggering. Earth orbits the Sun at 67,000 miles per hour. The Sun orbits the Milky Way center at 490,000 miles per hour. The Milky Way moves within the local group at about 200,000 mph. Yet all of these are small compared to the local group's bulk motion. We are fleeing the local void at roughly 600,000 miles per hour, or 250 kilometers per second. Every second, our galaxy travels 250 kilometers away from the void center. In an hour, that's 900,000 kilometers. In a day, 21.6 million kilometers. In a year, we traverse nearly 8 billion kilometers in addition to what cosmic expansion alone would cause. This motion is not expansion, it's our journey through space. The difference is crucial. Cosmic expansion stretches space itself. Galaxies recede because the space between them grows. They aren't moving through space during expansion. Peculiar velocities, however, are different. These are real motions. Galaxies moving through space driven by gravity. Dense regions pull galaxies toward them, while underdense regions push galaxies away. In effect, the void acts like negative mass, gravitationally repelling nearby objects. Measuring this velocity requires careful analysis. Observations show the local group moving at roughly 630 kilometers per second relative to the cosmic microwave background CMB. Frame what's called the CMB dipole. This creates a slight temperature difference between CMB photons approaching from ahead versus behind. But this total velocity contains multiple components. Part from the Milky Way's motion within the local group, part from the local group's motion within the local sheet, and part from the local sheet's motion within larger structures. Each must be separated. Astrophysicists do this by measuring velocities of nearby galaxies. Galaxies sharing our motion are part of the same bulk flow. Those moving differently respond to other influences. Catalogs of peculiar velocities for tens of thousands of galaxies reveal the layered structure of cosmic flows. The local void evacuation contributes about 250 kilometers per second to our total velocity. This isn't the fastest cosmic flow. Massive structures like the Great Attractor can pull galaxies at over 1,000 kilometers per second, but The local void flow is significant because we are directly participating in it. Our motion affects every observation we make. When we measure a galaxy's redshift, we are doing so relative to a frame that is itself fleeing the void. A galaxy receding at 5,000 kilometers per second due to cosmic expansion will appear slightly less redshifted if it lies in the direction we are moving, and slightly more if it lies opposite. This creates directional biases in expansion measurements. While these biases partly cancel across the sky, they do not entirely vanish. The void's influence goes beyond our peculiar velocity. Its gravitational effect slightly alters the local expansion rate. Space inside the void expands faster than average. Both effects' peculiar motion and modified expansion must be accounted for when interpreting observations. This is technically challenging. Many expansion measurements subtract our motion using the CMB dipole and interpret the rest as pure expansion, assuming the rate is uniform everywhere. If the void modifies local expansion, this approach is insufficient, as the void's expansion can masquerade as additional peculiar velocity. Disentangling these effects requires detailed modeling of void dynamics. Such models exist, but they depend on parameters like the void size, density profile, and our position within it. Uncertainties propagate into measurements. Future observations will improve this. Larger samples of galaxies with measured peculiar velocities will map the flow field more accurately. Better measurements of galaxy distributions will pin down the void's properties, and simulations incorporating voids will predict observable signatures. Within a decade, the local velocity field should be understood well enough to make precise corrections. For now, we know we are fleeing the void at extraordinary speed. This motion is real, measurable, and consequential. It affects how we perceive the universe's expansion and is essential to resolving the Hubble tension. Before atoms existed, the universe rang with acoustic waves, not sound as we know it. No air to carry vibrations, but pressure waves in plasma. These alternating compressions and rarefactions traveled at incredible speeds during the first 400,000 years, when the universe was a dense fog of protons, electrons, and photons behaving like a fluid. Denser regions had higher pressure, driving expansion, while gravity pulled matter together. This cosmic competition created oscillations, like pressing and releasing a spring. Overdense regions compressed under gravity until pressure pushed them apart, expanded past equilibrium, then were pulled back. Each cycle took hundreds of thousands of years. Waves propagated outward from every initial density fluctuation at roughly 58% of light speed. These waves weren't as fast as light because matter's inertia slowed them. Dark matter complicated the picture. It doesn't interact with photons, so no pressure affects it. Dark matter responded only to gravity. While normal matter and photons oscillated, dark matter stayed put at the center of each fluctuation. This created a structure, a concentration of dark matter at the origin, surrounded by a shell of normal matter and radiation at the distance the sound wave traveled, and another shell from the next oscillation cycle. When atoms formed, everything changed instantly. Electrons and protons combined into neutral hydrogen. Photons decoupled from matter, and the pressure supporting the waves vanished. The oscillations froze mid-cycle, locking the pattern in place. Dark matter concentrations remained at the origins, and the matter shells stayed at the distances they had reached. Over billions of years, gravity pulled additional material into these patterns. Galaxies formed preferentially at the overdense locations, both the origin points and the frozen sound wave shells. This left a signature. Galaxy clustering shows a slight preference for certain separation distances. Pairs of galaxies are slightly more common at roughly 500 million light-years apart than at slightly smaller or larger distances. This is the Baryon Acoustic Oscillation, BAO signal. The excess is subtle jazz, a few percent, but detectable with large galaxy samples. Surveys cataloging millions of galaxies reveal the pattern clearly. Why does this matter for measuring cosmic expansion? Because a separation distance is precisely known. The sound wave traveled for a specific time, at a specific speed, both determined by physics. We can calculate the distance the wave traveled before freezing, about 450,000 light-years at the time. But the universe has expanded since then. That distance has stretched along with everything else. Measuring what it looks like today tells us the total expansion factor. Observing galaxies at different distances and measuring the BAO scale at each distance allows us to trace the universe's expansion history. Nearby galaxies show less expansion, distant galaxies more. This method doesn't require keyfights or supernova. It relies purely on geometry and the physics of sound in the early universe, making it a powerful cross-check for other methods. Here's where the void comes in. BAO measures expansion between galaxies. If galaxies near us are evacuating the void, Their motion adds to their redshift. The bow distance then appears slightly larger than it should based on expansion alone. The distortion is small, but measurable, varying with distance. Galaxies deep inside the void show maximal distortion, while galaxies beyond the void's edge show minimal effect. By measuring bow at different distances and comparing to predictions, astronomers can map the void's influence. Indra Nilbanik analyzed 20 years of bow data from multiple surveys. The measurements showed systematic patterns, consistent with the local void, and the void model explained the data far better than a uniform model, compelling evidence supporting the existence of the KBC void. BAO provides an independent test of the void hypothesis. It doesn't rely on Kiphites, supernova, or CMB predictions. It's pure geometry based on well-understood early universe physics, offering a cosmic ruler stretching billions of light. When atoms formed 380,000 years after the Big Bang, sound waves froze at a specific distance called the sound horizon, 450,000 light-years then, now roughly 500 million light-years due to cosmic expansion. Every bow signal in the universe stretches by the same factor. Comparing the scale at different cosmic epochs reveals the expansion history. Galaxies at redshift 0.5 showed the universe when it was about two-thirds its current age. Their bow scale appears smaller due to less prior expansion. Galaxies at redshift 1 show the universe at half its current age. Their scale appears even smaller. Plot these measurements over cosmic time, and you reconstruct how expansion evolved. This method is elegant, relying solely on counting galaxies and physics from the early universe.